Hi ladies and gentlemen, this is Ms. Koken. We are back in Chapter 9. This time we're talking about dilations. Our objective is identify and draw dilations, and our vocabulary is dilation. Let's take a look at the warm-up. We have only one warm-up question, and it says, translate the triangle with vertices that are given for A, B, and C along the vector 2, 2. So I'm going to ask you to turn the video off and find the image of those pre-image vertices of the triangle, and then turn the video back on when you're ready to check your answer. See you back in a minute. Hopefully you didn't have any trouble using that translation vector and you were able to come up with the coordinates of the image. All right, a dilation is a transformation that changes the size of a figure but not the shape. The image and the pre-image of a figure under a dilation are what we call in geometry similar. In geometry, the term similar means something very specific. Similar figures have the same angle measures at corresponding vertices and proportional side lengths. We'll see more about proportions later in this lesson, but for right now, just think about that definition a little bit as we discuss all of these dilation figures or dilated figures. In example 1, we want to identify dilations and tell whether each transformation appears to be a dilation or not, and then of course we have to explain. So in question A, these figures are definitely not proportional, so they cannot be dilations of one another. Proportional figures look exactly the same except that one is smaller than the other, but they have the same proportions. So in the right-hand side, you can see that this distance and this distance is exactly the same, where on the blue one on the left-hand side, the vertical distance is much longer than that horizontal distance, so they're not proportional. When we come to the question on the right, these two triangles are exactly the same shape, just the blue one is bigger than the red one. So these are dilations of one another. Now let's take a look at the formal definition of dilations in the box. A dilation or similarity transformation is a transformation in which the lines connecting every point P with its image P prime all intersect at a point C called the center of dilation. So you can see in this figure, here's our center of dilation, and then we have a point P and a point Q. So C is the center of dilation. We have this segment, PQ, and we want to dilate it so that we have an image of the segment of PQ that is larger. And it's going to be, the way that we're going to look at this is the distance from point C to point P prime over the distance from point C to point P is the same for every point P. So every point is going to be dilated, or the distance between every point and every other point is going to be dilated the same exact amount. The scale factor K, so that means how much it was either stretched out by or shrunk by. The scale factor K of a dilation is the ratio of the linear measurement of the image to a corresponding measurement of the pre-image. In the figure, K, or the scale factor, is going to be the distance between P prime and Q prime, right here, over the distance from P to Q, which is the length of segment PQ. And that ratio, or the division, whatever number you get as a quotient, is going to be the scale factor. So we're going to look at some specific scale factors in some specific examples. Don't worry about this very formal definition, but you can look back on it for that idea of similarity and how it's all proportional. A dilation enlarges or reduces all dimensions proportionally. That's what we can have as our takeaway from the formal definition. A dilation with a scale factor K greater than 1 is going to stretch out or enlarge the original figure. A dilation with a scale factor greater than 0 but less than 1 is going to be a reduction. We can also call that a contraction. We might have called it in middle school a shrink. So we have two different kinds of dilation. We either have an enlargement, which is a scale factor greater than 1, or we have a reduction, which is a scale factor between 0 and 1. In example number 2, we want to be able to draw the image of pre-image WXYZ, this rectangle, under a dilation with a scale factor of 2. This means that when we compare the image and the pre-image, the image is going to have side lengths twice as long as the side lengths on the pre-image. And we're going to need a ruler for this. So we're going to start out by taking a look at what the length is from point P, that center of dilation, to point X. And whatever that distance is, we're going to double it and draw in point X prime. Now that we've got the location for X prime, we're going to do the same for the other points W, Z, and Y. When you're working in Notability, you don't have to use a ruler. What you can do is draw the segment and then make a copy of that segment and then attach it to the end of the original segment. In effect, making a scale factor of 2 by doubling the length of the original segment. So pause the video now, draw your twice as long segments from point P to points W prime, Y prime, and Z prime, and then turn the video back on so that we can take a look at what the image of the pre-image for quadrilateral or rectangle WXYZ looks like. See you back in a minute. So hopefully you didn't have any trouble making the image from the original rectangle pre-image. And you can see how in Notability it's pretty easy. For the next one, you've got a Now You Try. You are going to need to use a ruler. This one has a triangle, ABC, and this time what you want to do is create a new triangle, A prime, B prime, C prime, that uses a dilation factor of 1/2, which means you want each of the segments from point P, that center of the dilation, to the new points A prime, B prime, and C prime to be half the length of the original segments that created the original triangle ABC. So I'm going to have you pause the video once again, get out a ruler, and you are going to first start out by measuring the distance and drawing the segment from point P to point A, point P to point B, point P to point C. Measure half of that, and then you'll be able to draw the new points, A prime, B prime, C prime, connect those segments so that, or connect those points with segments so that you can create the new triangle. And turn the video back on when you're ready to check your answers. We see that the image triangle A prime, B prime, C prime it has segment lengths, I should say, that are half the size of the original image triangle ABC. And we did that with the scale factor. Again, you know, the idea is when we use a specific method, we get an image that is the same shape as the pre-image. This is not something to freehand. This is something that we need to use that point of dilation to help us out. All right, let's take a look at example 3 now. Example 3 reads, on the sketch of a flower, 4 inches represents 1 inch on the actual flower. If the flower has a 3-inch diameter in the sketch, find the diameter of the actual figure. So this is actually giving us a lot of information in the question, and we know that we have a scale factor that's been given to us where 4 inches represents 1 inch. And that means that on the sketch, where we have something 4 inches long, that means that the actual flower is only going to be 1 inch long. This is the perfect application for a proportion, which we learned back in pre-algebra. So we start out with what we know, which is 4 inches represents 1 inch, and then we're going to set that equal to the information that's given to us. So the flower has a 3-inch diameter in the sketch, and we want to know what does that represent on the real flower. So we've got our proportion now. And so you may remember that we drew these loops when we did a proportion, and we had 2 products to write down. So the proportion, the right-hand side of the proportion is going to be 4 inches times x, and on the left-hand side of the proportion, we're going to have 3 inches times 1 inch. Now at this point, we want to divide both sides by 4 inches so that we have x equals. So we end up with x is equal to 3 inches times 1 inch divided by 4 inches. And of course, we can see that we've got an inches unit in the numerator, an inches unit in the denominator, so we can divide that out 1 for 1. And then we're going to end up with a final answer of the actual flower's diameter is 3/4 of an inch. Because the next example, this Now You Try, is a little bit different than the original one, we're going to work on this together. So an artist is creating a large painting from a photograph by dividing the photograph into squares and dilating each square by a scale factor of 4. If the photograph is 20 centimeters by 25 centimeters, what is the perimeter of the painting? So I'm going to start by actually drawing a rectangle that will represent the photograph. And we know how to find the perimeter of this rectangle. We're going to start with the formula, like we always should, and it's going to be 2 times the length plus the width. So 2 times 25 centimeters plus 20 centimeters, which is 45 centimeters. So 2 times 45 centimeters is 90 centimeters. Remember that perimeter is a linear measurement, so we're not multiplying the 2 dimensions to each other, we're adding them to each other. This means that to go all the way around the photograph, it is going to be 90 centimeters. Now I'm going to draw a rectangle to represent the painting. Pause the video and do the same. And we know that there's a scale factor of 4, so where the photograph was 20 centimeters wide, the painting is going to be 20 centimeters times 4, the scale factor wide, or 80 centimeters wide. And the length of the photograph was 25 centimeters. Again, we're going to multiply by the scale factor of 4, and we're going to end up with a length of 100 centimeters. So we're only drawing this out to help us visualize what's going on here, but really we didn't have to do it, because what we could say is that the painting perimeter is equal to 4 times the perimeter of the photograph, which means we can calculate it using the photograph perimeter that we found of 90 centimeters. And when we multiply by the scale factor of 4, we get 360 centimeters, which is the perimeter of the painting. Okay, let's take a look at the formal definition of dilations in the coordinate plane. We see that it says, if a point P with the coordinates xy is the preimage of a point under a dilation centered at the origin with scale factor k, then the image of the point is P prime, and the coordinates of P prime are going to be k times x, comma, k times y. This is only because it's centered at the origin. Earlier we talked about scale factors being either greater than 1 or between 0 and 1, but if the scale factor of a dilation is negative, then the pre-image is rotated by 180 degrees. So we've got 2 different things going on. We've got a dilation going on, and we've got a rotation going on. So let's take a look at example 4, where we're going to use this information. Example 4 has instructions that say, draw the image of the triangle with vertices P, Q, and R under a dilation with a scale factor of -1/2 centered at the origin. So we've got 2 different things going on. That negative tells us we're going to rotate by 180 degrees centered at the origin, and the 1/2 tells us that we're going to have a dilation of 1/2. So the side lengths of triangle P prime, Q prime, R prime are going to be half the length of the triangle segments that create triangle PQR. So let's start by writing down the preimage coordinates and the dilation rule. Writing down the dilation rule always helps, because then you can see exactly what the changes to each coordinate are going to be. So we know that k is equal to -1/2, and the dilation rule is going to be, because we are centered at the origin, -1/2 x and -1/2 y. And that allows us to write down the image coordinates. 4 points P prime, Q prime, and R prime. And as I explained to you, when we are transforming a figure, we can work with the rule, the transformation rule, and come up with the new coordinates. However, unless we graph it, we can't see if we actually did it correctly. So it's a great check. So I'm going to ask you to pause the video now, graph the image and graph the pre-image, and preferably in different colors because they do overlap in this case. Turn the video back on when you're ready to check your image and pre-image work. See you back in a minute. Oh, and remember to label your points. See you back in a minute. Now that we've got the pre-image and image graphed, we can see that our coordinates are in fact correct with the rotation having taken place and the same shape, but obviously different sizes. And you've got, and now you try following this example, and I think you'll, if as long as you follow the model of the one that we just went through together, I think you'll be fine with it. So remember to start by organizing your work, working on the pre-image coordinates, the dilation rule, the image coordinates, following the dilation rule, and then graphing to verify that you have done it correctly. Turn the video back on when you're ready to check your answer. Okay, so this was the last example before it's time to do practice problems. Hopefully you were able to graph the pre-image and the image successfully, and you do in fact see the rotation and the dilation in our image. See you back in class.